It was a Tuesday. A gray, drizzly Tuesday on the River Thames. I was standing on a barge, looking at a set of blueprints that felt more like a treasure map to disaster. The chief engineer, a man with more degrees than a thermometer, had overlooked a single, tiny detail. A detail buried deep in the geotechnical survey. He'd assumed the riverbed was solid clay all the way down. He was wrong. A lens of soft, silty sand sat 20 meters below the surface, a hidden trap waiting to swallow our multi-million-pound project whole. This wasn't just a simple mistake. It was a potential catastrophe that could bring a bridge and careers crashing down. That single oversight could have cost the project an extra 10 million pounds and months of delays. It was a stark reminder of a fundamental truth I've learned over years of mucking about in places most people try to avoid. The real challenges, the truly dirty parts of any job, are almost always hidden from view. Underwater construction is the perfect example. You're fighting an opponent you can't see in an environment that wants you out. Every shovelful of mud, every bolt tightened, is a battle against immense pressure, blinding silt, and the constant, nagging threat of a leak that could undo everything in an instant. My job on that particular day was simply to watch and learn from the crew, tasked with building the foundation for a new bridge pier. These weren't office workers in crisp shirts. They were grafters, men and women who understood that water is relentless. They knew that to build something strong enough to last for a century, you first have to tame the river itself. Their work is a complex ballet of heavy machinery, brute force, and delicate engineering, all performed in a murky, unforgiving world. It's a job where a small error in judgment can have monumental consequences, as the chief engineer was now learning. The plan had to be redrawn. The team went back to the drawing board, their faces grim but determined. This is the reality of these colossal projects. It's not a smooth, linear process from A to B. It's a messy, unpredictable, and often dangerous struggle against the forces of nature. The public sees the graceful arches of the finished bridge, a testament to human ingenuity. They don't see the sweat, the mud, and the near misses that happen deep beneath the cold, dark water. They don't see the moment a young engineer points out the flaw that saves the day. And that's the story I'm here to tell. So why all the fuss? Why not just build the bridge pier directly in the water? It seems simple enough, right? Just get some divers down there, pour some concrete, and Bob's your uncle. Well, reality is a much wetter and more complicated beast. Trying to build a precise, robust structure underwater is like trying to assemble a Swiss watch in a washing machine during a spin cycle. The water is constantly moving, visibility is often zero, and you can't control the quality of your work. Concrete, the very backbone of modern construction, doesn't like being mixed with water after the fact. It washes away the cement, leaving you with a pile of useless sand and gravel. Imagine trying to lay bricks in a swimming pool. Every time you place a brick, the current nudges it out of place. The mortar you try to apply dissolves into a cloudy mess before it can even set. You can't see if your lines are straight or if the wall is level. That's the challenge, but magnified 1,000 times over. Underwater construction crews are battling not just gentle currents, but powerful river flows, tides, and immense water pressure that increases with every meter you descend. It's an environment that is fundamentally hostile to the act of building. Furthermore, the safety of the workers is paramount. Working underwater is one of the most dangerous jobs on the planet. Divers face risks from decompression sickness, equipment failure, and entanglement. Their ability to work is limited by the amount of air in their tanks and the extreme physical toll the pressure takes on their bodies. Asking a team of divers to construct an entire multi-ton bridge pier from scratch in these conditions would be impractical, incredibly expensive, and unacceptably dangerous. You simply cannot guarantee the structural integrity required for a bridge that will carry thousands of vehicles every day. So, engineers came up with a brilliantly simple, yet incredibly complex solution. If you can't work in the water, get rid of the water. It sounds like something a child would suggest, but it's the guiding principle behind one of the most important structures in underwater construction: the cofferdam. The goal is to create a temporary dry workspace right in the middle of the river. It's about creating a little bubble of dry land where it has no right to be, allowing builders to work as if they were on solid ground. It's a monumental task, but it's the only way to do the job safely and correctly. A cofferdam is essentially a temporary dam, a watertight enclosure built right in the river. Its sole purpose is to hold the water back so that a permanent structure like our bridge pier can be built in a dry environment. Think of it as building a giant, bottomless steel box, sinking it to the riverbed, and then pumping all the water out. Once it's dry inside, the construction crew can get to work. It's a simple concept, but the execution is a masterclass in heavy engineering. You are, after all, building a wall to fight a river, and the river always wants to win. The process begins with the installation of guide piles. These are strong steel posts driven deep into the riverbed, forming a template or a guide for the main walls of the cofferdam. They are positioned with pinpoint accuracy using GPS and lasers, because the entire structure depends on this initial framework being perfect. The guide piles act as a skeleton, ensuring that the sheet piles, which form the skin of the cofferdam, are installed in a perfectly straight line and in the correct shape, which is often circular or rectangular. This frame is critical for resisting the immense forces that the river will exert on the walls. Once the guide piles are in place, the real wall building begins. This is done using sheet piles. These are long sections of steel with interlocking edges, a bit like a tongue-and-groove joint on a floorboard. One by one, these sheets are driven into the riverbed, slotting into the one before it. A crane lifts each pile into position, and a special machine hammers or vibrates it down until it's firmly embedded in the soil, often many meters below the riverbed. This process is repeated, pile by pile, until the entire enclosure is complete, forming a continuous, solid steel wall. The interlocking design is the secret to the cofferdam's success. As each pile is driven, its edge locks tightly with its neighbor. This connection is what makes the wall watertight, or at least highly water-resistant. The goal is to create a barrier so effective that once the enclosure is complete, the water inside can be pumped out faster than it can leak back in. Building this steel fortress in the middle of a flowing river is the first major battle in the war against water, and it sets the stage for all the critical work that is to follow. How do you get a 15-meter-long steel sheet pile through dense riverbed soil? You might think the answer is a very, very big hammer, and sometimes that's part of it. But brute force alone is often not the best method. Simply hammering a pile can damage its top, a phenomenon known as piling head failure, and it can send shockwaves through the ground that might damage nearby structures. Instead, engineers often turn to a more subtle, yet incredibly powerful force vibration. The machine used for this is called a vibro hammer, and it works on a fascinating principle. The vibro hammer clamps onto the top of the sheet pile. Inside the hammer, a pair of counter-rotating eccentric weights spin at high speed. As they spin, they create intense vertical vibrations. These vibrations are transferred down the length of the steel pile, causing the soil particles immediately surrounding it to essentially liquefy. The friction between the pile and the soil, known as skin friction, is dramatically reduced. The soil temporarily behaves less like a solid and more like a thick fluid, allowing the pile to slide downwards with relative ease, aided by its own significant weight. This method is not only more efficient, but also much quieter and less jarring than traditional impact hammering. The constant hum of the vibro hammer is a familiar sound on these construction sites. It's a sign of progress that doesn't involve the earth-shattering bangs that can annoy the neighbors and stress the surrounding environment. The operator can carefully control the frequency of the vibrations to match the specific soil conditions, optimizing the process for speed and safety. It's a finessed approach to a task that looks like pure brute strength. Of course, sometimes a bit of extra persuasion is needed. If the pile hits a particularly dense layer of gravel or a stubborn boulder, the vibro hammer might be supplemented with an impact hammer to punch through the obstruction. But the primary workhorse is vibration. It's a clever use of physics to trick the ground into letting go. By agitating the soil particles into a frenzy, the pile can sink smoothly into the riverbed, creating the strong, continuous wall needed to hold back the immense pressure of the river and give the workers a safe, dry space to build. Before you drive a single pile or spend a single pound on steel, you have to do your homework. And in underwater construction, that homework means getting to know the ground you're about to build on. You can't just guess what's down there. As our chief engineer almost found out the hard way, assumptions can be disastrous. This is where geotechnical engineering comes in. It's the science of understanding what lies beneath the surface, and it is arguably the most critical step in the entire process. Without this knowledge, you are building blind. The investigation starts with taking soil samples. A specialized rig, usually mounted on a barge, drills deep into the riverbed. It extracts long cylindrical cores of the soil and rock from various depths. These cores are like a layered history of the Earth at that exact spot. They are carefully labeled, packaged, and sent to a laboratory for analysis. In the lab, scientists will test the samples for all sorts of properties: their strength, their density, their composition, and, most importantly, how they behave when they get wet and are put under pressure. These tests reveal the secrets of the riverbed. They tell engineers whether they will be driving piles into soft silt, dense sand, stiff clay, or solid bedrock. Each material behaves differently. Soft silt might not provide enough support, while dense gravel could be difficult to penetrate. The analysis determines how deep the sheet piles need to go to be secure and to prevent water from seeping underneath. It also tells the engineers how much weight the ground can safely support, which dictates the entire design of the bridge pier's foundation. This detailed soil report is the Bible for the construction project. It informs every major decision. It confirms whether a cofferdam is even feasible or if another method is required. It helps calculate the forces that will be acting on the structure, ensuring the design is robust enough to last for generations. Ignoring the geotechnical survey is like setting sail without a map or a compass. You might be fine for a while, but eventually, you're going to run into trouble. Knowing your muck isn't just good practice. It's the difference between a successful project and a very expensive hole in the water. Sometimes, a single wall of steel just isn't enough to win the fight against the river. In areas with very deep water or particularly troublesome soil conditions, the pressure pushing against the sheet piles can be absolutely immense. Plus, even with the best interlocking piles, tiny gaps can exist. Under hundreds of tons of water pressure, these small gaps can turn into high-pressure jets, basically turning the inside of your supposedly dry cofferdam into a muddy swimming pool. When this happens, engineers have to up their game and bring in the reinforcements. The solution is often a double-walled cofferdam. Instead of one ring of sheet piles, they build two, creating a space between them that can be several meters wide. This creates a much stronger and more stable structure, kind of like having an inner and outer fortress wall. The two concentric rings of piles are connected by steel tie rods to ensure they act as a single unified structure. This design provides a huge increase in strength and stability, but its real genius lies in how it deals with the persistent problem of leaks. The space between the two walls isn't left empty. It's filled with a granular material, usually sand or gravel. This fill material serves two crucial purposes. Firstly, its sheer weight adds to the stability of the entire cofferdam, helping it resist the colossal force of the water pushing from the outside. Secondly, and most importantly, it acts as a brilliant sealing agent. Any water that manages to seep through the tiny gaps in the outer wall has to then navigate a long and difficult path through the tightly packed sand. This journey saps the water of its energy and pressure. By the time it reaches the inner wall, it has been reduced to a harmless trickle, if it gets there at all. The granular fill effectively clogs up any potential leaks, acting as a giant, built-in filter. This double wall and fill technique is a far more robust way to ensure a dry working environment. It's more expensive and time-consuming to build, of course, but for deep, difficult, or long-term projects, it provides a level of safety and security that a single-skinned cofferdam simply cannot match. Once the cofferdam is built and the water is pumped out, the real test begins. The structure is no longer supported by water pressure on the inside, balancing the pressure from the outside. Now, the full, crushing force of the river is pushing inwards on the walls. Water is incredibly heavy, weighing about 1 ton for every cubic meter. A cofferdam standing in 10 meters of water has 10 tons of pressure pushing on every single square meter of its base. Without proper support, those flat steel walls would buckle and collapse in an instant. To counteract this immense squeeze, engineers install a system of internal bracing frames. These are heavy-duty steel beams, or whalers and struts, that run horizontally inside the cofferdam. The whalers are rings of steel that press against the inside of the sheet pile walls, while struts span across the cofferdam, pushing against the whalers. This framework acts like an internal skeleton, transferring the pressure from one side of the cofferdam to the other. The force pushing in on the left wall is used to resist the force pushing in on the right wall. As the water level inside the cofferdam is lowered during the pumping process, these bracing frames are installed at progressively deeper levels. The crew will pump the water down a few meters, install a level of bracing, pump it down a few more meters, and then install the next level. It's a carefully choreographed sequence. You can't just pump it all out at once and then try to put the bracing in. The walls would fail long before the cofferdam was empty. The pressure is simply too great. This internal cage of steel can make the workspace feel cramped and cluttered, but it is absolutely non-negotiable. Every beam and every bolt is a critical component in the battle against hydrostatic pressure. The design of these frames is a complex engineering calculation, taking into account the depth of the water, the size of the cofferdam, and the strength of the sheet piles. It's a powerful visual reminder that even when the water is gone, its presence is still the single biggest force that everyone is working against. It's a constant, invisible squeeze that must be respected. Even with a double-walled, internally braced cofferdam, there's another sneaky way water can get in from below. The river doesn't just push against the sides of the dam, it also pushes down on the riverbed outside. This pressure can force water to find a path down into the soil, under the bottom edge of the sheet piles, and then up into the dry area inside. This phenomenon is known as seepage, and it follows a path that looks a bit like the U-bend under your kitchen sink. If this seepage is not controlled, it can be incredibly dangerous. You can see this effect with a simple experiment. Take a clear plastic tub, put a divider in the middle that doesn't quite reach the bottom, and fill one side with water. The water can't go over the top, but if you put sand in the bottom of the tub, you'll see the water slowly seep through the sand, under the divider, and start to wet the sand on the dry side. Now, imagine this on a massive scale. The water seeping under the cofferdam exerts an upward pressure on the soil inside. If this upward pressure becomes too great, it can lift the soil, causing the bottom of the excavation to boil. The soil loses all its strength and turns into a quicksand-like slurry. This is a catastrophic failure. It can undermine the stability of the entire cofferdam, causing the sheet piles to give way and leading to a sudden, violent flood of the workspace. This is why the depth of the sheet piles is so critical. They need to be driven deep enough to make the seepage path as long and difficult as possible, reducing the pressure of the water that makes it inside. To manage the water that inevitably does get through, a system of pumps is put to work 24 hours a day, 7 days a week. Small channels are often dug around the inside perimeter of the cofferdam, leading to a collection point called a sump. As water seeps up through the soil, it flows into these channels and gathers in the sump. From there, powerful pumps continuously pump the water out and back into the river. This continuous pumping is a vital lifeline, keeping the upward water pressure in check and ensuring the floor of the work site remains stable and safe for the crew. With the cofferdam dewatered and the seepage managed by pumps, the final stage of foundation work can begin. The aim is to create a solid, permanent, and waterproof base for the bridge pier. The first step is to excavate the remaining soil from inside the cofferdam down to the required depth. Then, to create a truly unshakable foundation, structural piles, often made of steel or reinforced concrete, are driven from inside the cofferdam deep into the ground until they hit solid bedrock. These piles will transfer the immense weight of the bridge directly to the strongest possible geological layer. The next step is to create a seal course. This is a thick plug of concrete poured onto the bottom of the excavation. This plug serves two critical functions. First, it provides a final, definitive barrier against any further water seepage from below. Once the concrete cures, it forms a permanent, impermeable floor. Second, it locks the bottom ends of the sheet piles and the structural piles together, creating a solid, unified base. To pour this concrete, a special technique is required to prevent it from mixing with the residual water in the sump. This method often involves using a tremie pipe. A long pipe is lowered to the bottom of the excavation. Concrete is then pumped down through the pipe. The end of the pipe is kept submerged in the freshly poured concrete at all times. As more concrete is pumped in, it flows outwards from the bottom of the pipe, gently displacing the water upwards without mixing with it. The crew pours the concrete continuously until the entire floor is covered to the required thickness, creating a single, massive, monolithic slab. Once the seal course is cured and is rock solid, the final pumps remove any remaining water, and for the first time, the inside of the cofferdam is truly bone dry. Now, the crew can build the bridge pier itself. They construct a steel reinforcement cage, or rebar, on top of the concrete base and erect formwork to create the desired shape of the pier. Finally, high-quality, durable concrete is poured to form the pier. This structure rises from the secure base, up through the bracing frames, and eventually emerges above the waterline, ready to carry the weight of the bridge and withstand the constant force of the river for the next 100 years or more.